Hello, everybody. Good afternoon. It's a pleasure to have you at this presentation, this webinar on home energy production. Well, in fact, renewable energies and how to integrate them in a home energy system. So we are expecting about 50 people this afternoon. So we will be waiting a little while for everybody to join. While we are waiting for them to join, let us introduce ourselves. Gonzalo, please, first.
Well, so we'll repeat. So for this webinar, we're going to be showing you several camera views, PowerPoint presentations, and some software. So to do so, just click in the image you're looking right now to make it full screen, and that's it. With that, you're going to be able to follow all the webinar that we have. I am going to be handling the chat and all the questions. If there's any question I'm not able to answer right away, I will pass it to Christian.
Thank you, Gonzalo. So my name is Christian Remillard. I'm working here at Festo Didactic Canada as a trainer and a pre-sales engineer. So I will be with you presenting to you the EMS system that we have just in the back of Gonzalo there today. And we'll see how it can be used to teach renewable energies and the power electronics systems that are required to be able to integrate these energies in a home energy production system. So while we are waiting for everybody to join again, as Gonzalo told you, make your webinar, GoToWebinar full screen, and also take some time to familiarize yourself with the interface. You will see that you have a hand button. So if we ask you to vote on something, to say yes or no, raise your hand. You just click on this button, so we will see that you have raised your hand. And you will also see that there is a chat tab and a question tab. So if they are just appearing as a gray tab, you just need to click on the little triangle on the left to open the tab and see content there. You will also see that I have provided in the it's not download, how do they call it? The handout section, that's it. So you will see in the handouts that I'm providing you also with a file, which is a PDF of the exercise that we'll be doing today together. So it's extracted directly from our manual, from our instructor manual, and it's exactly what we will be doing together today as a demonstration. So it will give you an idea of the amount of information we provide in our manual, and it will allow you to follow really easily what I will be doing here. So just before we start, I will ask you a few questions through polls that I have prepared, just to know your knowledge level of the topic at hand. So how much do you know this topic? And depending on the amount of the answers, this will allow me to focus more or less on different section of the presentation. So the first question that you will see in the polls, right there. So the first, you select the first poll, drop down. So the first question I'm asking you is, how much do you know about the solar power and photovoltaic cells? So again, it is for me to judge if you have a technical background in this topic, or if it's not the case. We'll present differently. Some of you, I don't know if GoToWebinar has fixed this little problem they had, but some of you might not be able to answer. I'm sorry, you might try to click on the answer, and that doesn't record your selection, but many of you will be able to answer. Whoops, I just lost the sound. Can you hear me? Okay, there's no echo anymore. Have you shut off your...
I turned off Gonzalo's mic.
You did turn off Gonzalo's mic.
Yeah, I just did.
Thank you. Yes, so Gonzalo, indeed, if you're not speaking, you should keep your mic off, so we lose this echo. Yeah, exactly. because they were hearing me through your mic. Thank you. So yes, how many answers have we got, Gonzalo? Okay, and how many people answered out of all the attendees we have? 70%? Oh, okay, so I think it's getting better. The feature is getting better. Thank you. You can go to the next poll, Gonzalo. About this one will be about wind power. So to know how much you know about wind turbines. So while you answer, the goal of the presentation today will be to show you how to teach photovoltaic technology, wind turbine technology, and also how to integrate them in a fully fledged home energy production system. All of this will be done with our EMS system that I have here in the back. So I will show you the various modules that are required to be able to accomplish these different exercises. We will have time only to do one exercise, but an exercise that, as you will see in the PDF I shared with you, an exercise that comprises really many different steps. We won't go through them all, but the most important ones. So what is okay, good. So I have more people who know about wind power than solar. That's good because we will spend more time on the wind side of things than solar today. And finally, one last poll to know if you know anything at all about integrating these technologies in a home energy production. So maybe some of you have at home a solar panel connected to a battery with an inverter and a battery charge controller. So maybe you already have that at home. Maybe you teach that. So just let me know if you know a little bit about this topic. Perfect. So this will be a great portion of the training then of the webinar to show you. You will learn a little bit of stuff about how a home energy production system is set up. So good. Let's start with the presentation itself. I will switch to PowerPoint, to my PowerPoint, and I will present to you quickly a glimpse of who is Festo, what is this company, what is Festo Didactic doing as part of Festo, and then we will dive right in the topic of today. So, but the image you see there is taken in one of the halls of our home office in Denkendorf in Germany. So this gives you an idea of the kind of, and you will recognize also the Festo look with everything being white, gray, and blue. This is the signature of the company. So Festo Automation is a group that started in the 50s, initially to build wood tools, but eventually it diversified itself into automation. That became a really world leader in automation technologies. So pneumatics, hydraulics, sensors, actuators of all kinds. The turnover of the company is around 3 billion euros each year. We are active in almost 200 countries with 300,000 customers, 21,000 employees worldwide, many patents. Every year we innovate with about 100 new patents that are recorded. So this gives you an idea of the size of the company. So this is Festo, the automation group that provides solutions to our customers, automation solutions to our industrial customers. But Festo also has a didactic branch, which is called Festo Didactic, which produces training systems for technical training. So training systems that are bought by customers to equip their labs and that they will use with their students to teach the fundamentals of automation, electrical engineering, and industrial trades, as we will see in a moment. So the good thing about having these two sides at Festo, the industrial side and the education side, is that in this way we are really able to promote the productivity of our customers. We promote the productivity of our industrial customers by providing them with machines that are really performant, and we improve the productivity of our customers also by providing them with trained technicians, because we train them on the equipment that we provide, that we produce ourselves. And just to give you a quick overview of the different fields in which we produce training systems, so you will see that Festo Didactic produces training systems in many different technical fields, from radar and telecom, wiring, sorry, this slide is in French here, industrial maintenance, electricity, electronics, HVAC, refrigeration, softwares, mechatronics, and automation, renewable energies, as we will see today. So we will spend now the next 30 minutes on the topic of home energy production and how it can be taught with the system that I have right behind me. Can you give me a picture-in-picture, please, Gonzalo? Thank you. So let's start with home energy production. So what you see here is the course tree that of all the courses that are available on our EMS training system. So each box you see there is a separate course that comes with its own manual, so student manual and instructor guide. Each course comes with that, and also comes with all the hardware modules required to perform all the exercises that are presented in these in the manual for this specific course. The course tree is laid out in such a way that the most basic topics are at the top. So DC power circuits, DC power electronics, AC power circuits, single phase, three phase, solar power, wind power, and then going down, we start talking about more advanced topics like power electronics, DC, AC, single phase, three phase, power factor, compensation, power distribution, and transmission, with transmission lines. And then we get at the bottom of the tree with the really more advanced topics like the smart grid technologies, sorry, SVC, STATCOM, HVDC, etc. So the tree is built this way to show that, okay, you must first master the topics at the top and then slowly make your way down in the tree. The boxes that are highlighted in blue here are the ones that correspond to the topic that we will be talking about today, home energy production. So to be able, for a student to be able to understand everything that is presented in this home energy production course, which is the blue box at the lower left, you can see that the student needs knowledge in all the previous topics. So DC power circuits, power electronics, lead acid batteries, wind power, solar power, and some AC, also power electronics. So let's start with solar power and how it can be covered with our system. So first of all, I will show you the content of the course on solar power. So 7 exercises to cover it all. First exercise about the diode, because a photovoltaic cell is some kind of really special diode. So we start with refreshing the knowledge of the students about the diode. Then we dive into the solar panel. And then we discuss what impacts the performance of a solar panel. So the effect of temperature, the effect of shading on the solar panel, the effect of orientation, and the effect of insolation, so the amount of sun falling on the solar panel. So all of these are treated in separate exercises. So as you can see, we go through all these topics theoretically and, of course, experimentally also, by providing them with an equipment that will allow us to test all of these all this new knowledge. So just a few screen capture from the manual, some images taken in the manual. So here showing what is a photovoltaic cell, how it works, what is the equivalent electric circuit, how we can combine multiple cells together to achieve to get a photovoltaic module that will provide us with a certain amount of voltage and current, how they are integrated in full solar panel. And then also presenting the voltage versus current curve of a typical photovoltaic cell, showing that there is a point where you have maximum power extracted from the cell, showing the impact of insolation, of illumination levels on the performance of the photovoltaic cell. So as I say, these are only a few images I've taken out of this manual to give you an idea of the coverage that we provide in our manuals. There is much, much more in this manual. And then once we have presented the theory that we wanted to show to our students, we propose them an exercise to be performed with the physical module. So here I will be presenting you the actual module that you see there on the screen in my PowerPoint. So, yes, thank you. So this is our photovoltaic panel. You might be surprised, you might have seen competitive products that are full-size photovoltaic panels that you can buy for your house at the hardware store. In our case, we decided to go with this really small format for our lab equipment. Why? Because a photovoltaic cell is by definition not really efficient. It only converts about 10% of the light falling on it into electricity. And then to produce this light, nowadays it has changed with the DELs, but 10 years ago to produce this light, you needed halogen lamps, which were really not performant, okay? About 10% also of the electricity going in the lamp producing light, and the rest being lost as heat. So to power a full photovoltaic panel in the lab, it took back then between 10 and 20,000 watts of lamp to power the full panel, which makes no sense. Of course, you cannot have that amount of lamps in your lab. So we decided to go with this small format. This is a simple 2-watt photovoltaic panel. So you will get 2 watts of electricity out of it, but it is a completely functional photovoltaic panel with 2 separate modules that you can connect in parallel or in series, depending on if you want more current or more voltage. Then it comes also with diodes on the top here that will allow you to do some experiments with these to bypass the certain modules when they are in the shade, for example, or prevent the battery from discharging through the panel during the night. It comes with its heat dissipation at the back here. So we will see that we will blow some air on this to keep the photovoltaic panel cool. It comes with its own thermometer to show you the temperature. So this is really a self-contained package that allows you to cover everything required in the classroom. So you can have only this module to perform all of the exercises. You can mount it on a tripod to put it under the sunlight to do your experiments, or put it anywhere you want. But the most convenient way to use it is with our test bench. So I will just insert it in the test bench here and show it to you. So here is the test bench, the complete test bench. So you can see that I have inserted the solar panel in it. So the test bench contains one halogen lamp that will light the solar panel. And on the other side, it has a fan, as you can see here, that will blow air on the panel to keep it cool. So complete solution, you can control the amount of light falling on the photovoltaic cell. You can turn on and off the fan to check the effective temperature on the performance of the panel. I just wanted to present you this theoretically. We won't do an exercise with it because we have much more to do with the wind turbine behind me and the power electronics, but know that there is a complete solution here to teach solar power. Any questions, Gonzalo?
You're fine.
No problem, perfect. So let's dive now into wind power. So same thing here, I will quickly present to you. Sorry, Gonzalo, can I go back to my PowerPoint? Thank you. So wind power, same thing here. I will present to you quickly the content of the manual that goes with our wind power course. So 4 exercises, one which talks about the voltage versus speed characteristic of a wind turbine generator. A second exercise talking about the torque versus current flowing through the turbine, the generator. Third exercise about power versus wind speed. So sorry, wind power versus wind speed. And finally, how to store the energy produced by the wind turbines in batteries. So again, just a few images taken out of the manual showing to the students why is it so important to have a huge wind turbine. Okay, why is it important to have the blades so long? Well, it's because of course you will capture as much energy as the amount of energy you will capture is proportional to the area of the wind turbine that the wind falls on. So the larger the area, the more power, of course, you gain. And of course, the faster, the stronger the wind, also the stronger the higher the amount of energy. So here we present to the students the full equation to calculate the amount of wind power, which is proportional, as you can see, to the rho being the density, the air density, A being the area, the cross surface area of our wind turbine, V being the wind speed, and as you can see, it is to the power of 3. So as the wind speed increases, the amount of power contained in the wind increases exponentially. We also present the fact that if you want to be able to extract the maximum power out of the wind, you need to be able to follow the maximum power point, which is not at a specific wind speed or at a specific rotation speed of the turbine, but you have to find the exact point, the exact current that flows through your turbine that will allow you to extract the maximum power out of the wind. Whoops. Now let me introduce you our wind turbine generator controller module. So first, no, Gonzalo, let's stay please on this image for the moment. So here you see the front plate of our wind turbine. So you can see that there is a lot that is provided in this single module. But first of all, you will see at the upper left of the module that you have the 3-phase output. So the output out of the 3 coils of our generator that is available right there. Then underneath that, you see that we have a diode bridge that will allow you to rectify this 3-phase AC voltage to a single DC voltage at the output. We provide you with resistors to be able to load the generator to test it. And finally, in the upper right corner, you can see that there is a controller, which is a battery charge controller, to which you can control the 3-phase output of the wind turbine, and on the right side you connect it to the battery that you want to charge. This is typical of a home installation where you will have your wind turbine connected to the battery to charge it. So now, yes, let's look at the module itself. Gonzalo, can we zoom on this? Thank you. Perfect. So here you can see the wind turbine module, same thing that I had before, except that I have a few wires connected for the upcoming demo. I will show you that inside of this, what you have is simply a generator, which is hidden in a box. but you can see here that it is tied to this sprocket here that will allow me to make a turn to produce electricity. What will make this turn to produce electricity? Well, if I was outside, I would have blades, rotor blades connected to this to make it spin in the wind. But since I am in the lab, I need to be able to have this spin under my control. And for that, I will need my 4-quadrant dynamometer just beside here. Can you turn the camera a little bit, Gonzalo? Thank you. So this module here is what we call our 4-quadrant dynamometer. So it will simply act as a prime mover for my wind turbine. So maybe you can see that there is a timing belt here between the two that ties the two. So when this turns, both turn at the same time. Okay, so I will control the behavior of this dynamometer here to achieve a specific speed, to simulate a specific wind speed, a specific wind density and type of wind turbine. So this will be able to emulate all that, driving the generator as if it was driven by a real wind turbine. So we will see how we can achieve that with the software that we use to control this unit. So let's dive into home energy production, and we will see in the context of the exercise how to use all of these modules there. So first of all, the table of contents for this specific course on home energy production. First exercise about a standalone home energy production. So when we are talking of a standalone home energy production system, we are talking about a system that is not connected to the power grid. So you will find that sometimes in the woods cottages, that do not have access to the grid. So they want to be independent. So they will have their own solar panel, their own wind turbine connected to their system in the cabin. And there they will be using the energy they produce locally, not being able to exchange any energy with the power grid. So this is the first exercise, and this is the one we will be doing together today. Then following that, we have the single phase grid tied inverter. So in grid tied meaning that now in this exercise, we simulate being connected to the power grid to be able to exchange power with the power grid. If we produce more power than we need locally, we can sell this extra power to the power company. And if we don't produce enough because it's the night or there is no wind, then we will be able to draw some power from the power grid to power our local applications. Third exercise about grid-tied home energy production using solar or wind power inverter without DC to DC converter or with DC to DC converter. I'm not going into these details, but these represents all the different kinds of installations that you can find in a home energy installation. Finally, large-scale energy storage, a step in the implementation. So how to store at a larger scale the energy produced by all these renewable energy devices. So quickly, some pictures taken again from the manual to show the importance of home energy production, how nowadays more and more houses are producing power for their own use and also to sell this energy to the power company. And one of the leaders in that sense is Sweden. In Sweden, they have lots of local energy that is produced that is exchanged with the grid. So of course, this releases the power company of having to provide the energy for the whole grid because it can count on all these various sources to provide the power to the whole grid. Yes. So so this is for the first exercise that we will be doing together, standalone home energy production. We have always a theoretical discussion at the beginning, and then we dive into the exercise. So quickly, I will show you here what we will be achieving in this exercise. Can I see? Yes, you can see my mouse here. So you can see that we have a choice of having two different types of sources to our system, either solar or wind. This will be connected to a battery to charge the battery or keep it charged. And at the same time, in parallel, it will be connected to a boost chopper. What is a boost chopper? It's a power electronics device that can take a certain voltage and boost it up to a higher voltage. So of course, our battery here will be at a much lower voltage than 220 volt if you're in Europe, or 120 volt if you're here in North America. So the battery typically will be at 48 volts. So you need to boost that up to 120 volt or 240, depending on where you are in the world. So this is the goal of the boost chopper. And then once you have this DC voltage, you need to invert it. So you need to, with an inverter, to convert it to AC using either a single phase or three-phase inverter, as you can see here. So this is the role of the inverter, to produce AC out of DC. And then with this AC, you will be able to power your local loads, your fans, your microwave, your lights, etc. A few mathematics to determine the amount of the voltage we need on the DC side to be able to produce 220 volt on the AC side. So just to show you the kind of information, again, that the students get out of these courses. Voltage feedback loop. So here, to make sure that no matter what is the amount of voltage at the battery, because the battery, of course, gets depleted, and as it depletes, the voltage gets lower and lower. But we want the voltage at the output of our booster, of our boost chopper, to remain constant to power the loads on the other side. So we need this voltage feedback loop, which will read the current voltage at the output of the chopper and send this information to the feedback amplifier and the comparator that will compare the current value to the value that is required, let's say 345 volt. And based on this information, we'll be able to increase or decrease the voltage output at the DC chopper output. And here the complete circuit here. So we have the section we just saw, the boost chopper, and the part on the right side here is about the single phase inverter that will take the DC power here in the middle and convert it to AC to power our AC loads. So this is the complete circuit that we will be putting up together now. So if you can switch me here, maybe a closer view to the modules, Gonzalo. Thank you. Okay, so I will quickly show you here which part is which and how they are connected. Of course, this looks like many, many wires, and in fact, there are quite a few, but this is for the student to be able to, at the same time, really understand what he's doing. If the student is a future electrical engineer, he needs to understand how the power flows in the circuit, which control units are required, what are the kinds of loads that are required, and all that. So this is exactly what this kind of exercise will teach him. So first of all, starting with our wind turbine that I've just shown you, you will see that I'm connecting the output of the generator to the input of the battery charge controller here. So I will be able to charge my battery. Then on the other side, of course, I need to connect my battery. But first, before going to the battery itself, I go through this module here, which is our data acquisition module. So that's why there are so many wires connected here, because this is the module that we will connect our voltages and currents to be able to measure them and display them in our software. So I go to the data acquisition module to record the amount of current and voltage coming out of my battery controller, charge controller. And then from there, I'm going to the battery here. So this is my battery, 48 volt battery that I will be able to charge and maintain, keep charge with the wind turbine generator. Then on the other side, what do we have? So once I go through the output here, I need to send the power to my, if we can go back to the schematic, Gonzalo. So you will see here that out of the battery, I need to go to a transistor that will do my chopper, that will implement my chopper to produce a higher voltage from this 48 volt DC. So if we come back to the unit here.
A quick question, Christian, because
Yes.
it's related. I have a question from the audience. Why we need to boost the DC voltage from the batteries?
Yes, thank you. So let me go back quickly to my PowerPoint, Gonzalo, please. Okay, so as I was explaining to you, the battery only produces about 48 volts typically, while on the DC bus side here, the voltage that we require to be able to produce a AC power of 220 volt here, or 120 if you're in North America. So the DC voltage I need is, according to this equation here, equals to 345 volt if I want to produce 220 volt AC at the output, or in our case for 120 volt, we need to produce about 200 volts. So we need 200 volt of DC voltage at the input of our inverter. So to go from the 48 volt of the battery to the 200 volt that I need here, I need this boost chopper that will bring up this voltage up. Any other question?
Just question regarding your presentation. Will it be made available? I mean, your PowerPoint. There's one document that's available now, but it's just for exercise 1.
Yeah, the PowerPoint, I still need to put some work in to be able to make it shareable. But yes, it can be shared if you want to. Just write to us. You have the email address. If you want a copy of that, we can make it available to you. But most of what is important for today is really in the PDF that I have provided you.
And there's one last question.
Yes.
For now, do you have virtual labs?
That's a really good question. So yes, indeed, for this EMS system that I am presenting to you, we do have a simulator, which is called LVSIM EMS. And in fact, many of you have heard about it over the last few months, because during the pandemic, we had made this, of course, the pandemic is not over, but let's say during the first stages of the pandemic, we had made this simulator free of charge for you to help you in your distance teaching. So LVSIM EMS is the simulator of this system. It does not do everything that this system allows to do, and in fact, the things that I am showing you today are not available. Unfortunately, most of them are not available. So renewable energies are not covered in the simulator, and the power electronics that I'm now showing you is not covered either. Okay, but it covers everything else that the system allows to do. So transmission lines, motors and generators, AC circuits, DC circuits, power factor correction, and all that. All of these topics can be taught and tested with this simulator. So we can make available. We will make available to you the address to this to the web version of the simulator. Gonzalo, if you can copy that in the chat box, the web address of LVSIM EMS. Okay, so that I'm skipping here, and now let's dive into the procedure because time flies. So what we will be doing here is we will operate the single-phase standalone inverter with the wind, as we just saw. So in this circuit here, no, the PowerPoint, please. In this circuit here, you can see the full circuit that I was just showing you. So with the wind turbine on the upper left, the output of the wind turbine going to the wind turbine controller, which will be connected to the battery on the right, and then to the DC chopper completely on the right. And then the circuit continues on the second line, where we, out of the chopper, we go into the inverter that is implemented with 4 transistors. And finally, out of this, we go through a filter and the load, which is a simple resistance on the far right, which represents the load of our that we are powering with the circuit. So yes, just quickly here, come back to this closer view. So as I was telling you, out of the wind turbine, out of the battery, I go to my transistor module here, which will implement the DC chopper and also the single phase inverter. So we have 6 transistors in this module, so it can combine both functions in a single module. And out of that, we go to the filter here, and out of the filter, finally, we go to the resistive load at the bottom here. So we have a module to implement a resistive load, which is, sorry, we don't see it on the camera. We should have another, yes, here. So with this module here, which is our resistive load module, we can change the value of the load to see the impact on our inverter. So let's start the whole thing here. I will now switch to my computer and launch our LVDAC EMS software. So this software is, I might need to reconnect. This is powered, this is powered. Reconnect. Yes. Okay, so this piece of software you see here allows me to control 2 units that I just presented to you. The data acquisition unit I told you that I use to measure voltages and currents, and also the dynamometer that I told you I would use to make my wind turbine generator spin to produce power. So this dynamometer will be simulating basically the wind turbine rotor to which the generator would normally be connected. So you can see here that I have my wind turbine emulator window. And in this window, I will be able to tell my 4-quadrant dynamometer how to behave. So I'm asking it to behave like a wind turbine emulator. I want the initial wind speed to be 9.5 meter per second. I want to emulate a specific air density, a specific type of wind turbine, and that's it. So if I'm satisfied with that, I can launch the wind turbine here and my generator will start spinning. But first, I'm showing you on the left side here my meter window. So in the meter window, I am currently displaying a few voltages and currents. E1 and I1 are the voltages and current out of the battery. Okay, so we can see that there is no current for the moment because there is no load connected yet, but I can see that the voltage of my battery is 49.78 volt. On E2 and I2 on the right side is the voltage and current at the load, so at the resistance that is connected on the far right of my circuit. And finally, at the bottom are the corresponding powers. So power coming out of the battery and power going to the load. So let's start the wind turbine here. I will get closer to it so you can hear it spinning. So as you can see, the wind turbine is now spinning, and we can see that in the meter here. So if we go back to the computer screen, you can see here now that I have a current of 2.3 amps positive, and this gives a power of minus 150 watts going to the battery. So the fact that it is negative tells me that the battery is currently being charged by the generator. Okay, it's not, the battery is not producing power, it is receiving power from the generator to be charged. On the load side, I still have nothing because the load is connected on the other side of my chopper, which I have not, chopper inverter, which I have not powered yet. So I will, just to show you here that if I change the wind speed, if you were here, you would hear the sound of the wind turbine slowly decreasing, and you can see that the current is also decreasing. The current that I'm feeding to the battery is decreasing with the wind power. On the wind turbine window here, you can see that we are constantly indicating the speed, the rotation speed of the wind turbine, the torque, which is the amount of mechanical strength that the turbine must provide to keep spinning, the amount of mechanical power corresponding to that, and the amount of energy that has been produced since I pressed the start button. So we can see that all of that makes all the information really clear for the students to understand what is happening. I will now shut that off and present you the last part of our demo here, which is about the single phase standalone inverter. So this, as you might recognize this circuit, that's exactly what we just saw in the slides. So once again, we have the battery on the left side, the boost chopper, the inverter that will convert this DC voltage to AC voltage, and then finally this will be connected to the resistor here. So now I will press the start button here. It will start sending triggering signal to the transistors here, so that they will start converting the DC voltage available before the chopper, basically, which is provided by the battery. So I will make that smaller. You can see also that we can control here the maximum power that the unit is able to provide, so that it is protecting itself. The minimum voltage that we want the battery to reach before we stop the circuit. We don't want to dry out the battery. The peak output voltage and the output frequency. So if you are in North America, you want to produce 60 Hertz. If you are in Europe or elsewhere in the world, you want to produce 50 Hertz. And finally, the DC bus voltage command. So what is the voltage I want to get out of my boost chopper here? All of this will be used by the circuit, the logic, internal logic here, to produce all of these values as requested. So now I launch the inverter. And you will see now that on the load side, I have things happening. So my wind turbine is not working. So right now, all the power that I have is coming out of the battery. And you can see that the voltage at the battery here is slowly decreasing because the battery is slowly depleting. It is currently providing 2 amps of current, and for a total power of 103 watts that is taken out of the battery. On the load side, I can see that the load sees a voltage of 108 volt with a current of 0.8, and this is AC. This was here DC. Whoops, this should be DC, in fact. This is DC here. And this here is AC, and the power 87 watts. So from 102 watts provided by the battery, 87 watts is going to the load, the rest being lost in the filter and the electronic circuit. But still, we can see that we have an efficiency of about 87, 88%, 86, 87%, which is not too bad. Okay, so that's good. You can see here on the oscilloscope in the back that I have configured to display let me change that here. Okay, so I have configured the oscilloscope to display the voltage and current at the load, so we can see that indeed it is receiving a AC voltage. So and I could measure, and the frequency is indicated down here, so we can see the frequency is really at 60 Hertz. And what we see here in purple at the bottom is the triggering signal I'm sending to the transistor of my chopper to produce more or less a more or less intense DC voltage at the output of the chopper. So this is all fine. So now let's combine the two, my battery and the wind turbine. So I will start my wind turbine again, and you will see that all the values here will change. So once again, now the current from the battery becomes a current to the battery. It becomes negative, and the power to the battery is also negative, which means that my wind turbine is now charging the battery, and at the same time, it is providing enough power to power my load on the other side here, as you can see. So currently, my wind turbine produces enough power to power the load and some more that is used to charge the battery. Of course, if the wind speed decreases here, I will try to make it, yes, so now you can see that there is almost no current flowing to the battery. So now the wind turbine is providing just enough power to power the load, and it has nothing left to power to charge the battery. And the battery is not either providing any power, it's fluctuating a little bit because the output of the wind turbine is not perfectly constant, but we can see that the battery is not drawing power nor providing power, everything being provided by the wind turbine. Finally, if I decrease the wind speed even more, which is now down to 6 meters per second, as you can see here, now we can see that the battery has to provide some power, 69 watts, combined with the 30 watts provided by the wind turbine to power completely the load. So you can see that this system can adapt perfectly to the actual wind speed, actual battery voltage, actual load, to constantly provide enough voltage and current to power the load. Yes. Where is the motor? Where? The module. Okay. Yes, excuse me, I might have shouted a little bit too strongly in your ears. So because here the wind turbine is a bit noisy, I will just turn it off. It will be easier for me. So the question was, where is the module responsible to implement the booster, so the boost chopper? It is this single module here that does it all. This module, let me clear off the cables a little bit. So this module here comprises 6 transistors. You can see the 3 top transistors here at the top, and underneath there are 3 more. Okay, so this module provides these 6 transistors. So why 6? Well, it's because when you do a 3-phase inverter, from a DC voltage to produce a 3-phase power, 3-phase voltage at the output requires 6 transistors. So that's why we have 6. But when you want to implement a single boost chopper, for example, a boost chopper only requires a single transistor. And a single phase inverter requires 4 transistors. So what we have here, what we do with our module, since we have 6 transistors, we split the module in 2. So the first portion of the module on the left here, so this portion on the left, has this one transistor here, which is used to, it's this one transistor here that is used to implement the boost chopper. And then the 4 other transistors are used together to provide, to implement the inverter, the single phase inverter, that, as you can see, the output of which, if we can zoom out a little bit, Gonzalo. So you can see that this is the output of my inverter, these 2 wires here, and you can see that they come here at the top to our filtering module. So if you look at the schematic in the PDF I provided you, you will see that the output of the inverter goes directly into the filter, and this is my filter module here. So yes, this single module implements both the chopper and the inverter. Any other questions? Okay, perfect. So globally, that's what I wanted to show to you today. Of course, we could go much deeper. If you look at the exercise that I have provided to you, there are many more steps that I have skipped, like, for example, testing the protection circuits that is implemented in our system. So like in a real inverter and a real battery charge controller, we are constantly monitoring the battery voltage to make sure that we do not deplete the battery, and the system will cut off drawing power from the battery if the battery battery voltage becomes too low. So that's one little part of the exercise that I've skipped to check that the circuit is working properly. And then there's another protection circuit that make sure that we do not draw too much power from the inverter, because of course an inverter has a certain power capacity because of the power rating of the transistors and all. So in our case, we set it to 250 watts, not to go above 250 watts initially, but you can change that and play with it and see that if you start drawing more power by increasing the load, if you start drawing more power than what is set as the set point for the maximum power, then the whole circuit shuts off to protect the circuitry. And this is done as part of the exercise also. The students have to experiment with that. You probably have noticed that the specific exercise I have selected here is really targeting electrical engineers, not electricians, because typically electricians will not want to dive that deeply into the internal workings of the equipment they are using. So basically they will have the components with them. They will have the industrial inverter, they will have the industrial battery charge controller, and they will wire them together in the circuit without understanding what is happening inside the inverter and the battery charge controller. This system allows diving into the modules and seeing how it is implemented using simple solid state devices like transistors. So the students really understand completely the internal working and how to implement one themselves out of basic transistor components. So the specific exercise is really focused to the electrical engineer. I would say that about half of the exercises available in the whole system are really for the electrical engineers, and the other half can be taught also at the technical, well, they can all be taught at the technical level, but typically what is required for a technician correspond to half of what is covered by this system, the other half being more going deeper into the theory of producing power and managing the power. Any other questions? Hello, check. Okay. One last thing I would like to talk to you about is our new platform, which is called Festo LX. I think that Gonzalo will be able to provide you also with the address to this new platform. So it is now available for you to register to the platform. Of course, it's not free of access, because what we provide on this platform is all of the content of our courses. Not all of our courses have yet been ported to the platform, but many of them already are. And that's the case of many of the courses that I have shown to you today are already ported to this platform. So having access to the platform gives you access to all of this curriculum, all of this courseware, presented in electronic format with questions for the students to answer. It also comes with an LMS, so a learning management system, that allows you to create your classes, record your student names, their grades and everything. So all of this is integrated to be a complete platform to manage your classes in technical fields. Of course, being Festo, we specialize in technical education, so the platform is really focused on that. So I suggest that you have a look at this platform. It might have something in it for you. And on top of that, we wanted this platform to be a collaboration tool. So it is possible, once you are registered on the platform, to upload some of your own material to this platform, to share with your co-workers and co-teachers the exercises that you have created yourself, because you will understand that with the kind of training systems that we provide being so modular and so expandable, that typically once you have a system like that, you will start creating your own exercises. We are providing you with about 200 exercises on this system, but it's only the tip of the iceberg. you will find many other ways of using the system, and you will come up with your own exercises. So this collaboration platform is a great tool for you to share with the rest of the world what you have done, and get from the rest of the world some new exercises also. No questions? So the recording of this webinar will be available to you, will be made available to you tomorrow at the same time. So in exactly 24 hours, you will receive an email with a link to visualize this recording of this webinar. So please feel free to share with the people who missed the webinar, the live presentation. And don't forget, before we close the webinar, to download the file, the PowerPoint file that I have shared with you. And if you have other questions, if you would like to get a copy of the PowerPoint I've used, which is simply excerpts of from our different manuals, please just send an email. Just send a request at the email that was provided with the registration email that you received, and it will be our pleasure to provide you with this information. You want to have a final word, Gonzalo? Well, I want to thank you again for your great support with the cameras and the questions and everything. I will give you some space. So we have our 2 meters.
So, well, thank you, Chris. That was very illustrative. Thank you guys for attending. So, as you know, we have a very large amount of webinars that are coming in the next weeks and months. So please keep in contact with us. We're going to show you a lot of very nice things. Thanks for watching.
Thank you. So in fact, yes, I had the last poll to ask them if they were planning to watch our upcoming webinars, but we're lacking time here. So thank you again for participating, and hopefully see you in an upcoming webinar. Bye-bye.